pulled up. It says match each kind of sequence on the left with an example on the right. This gives us an opportunity to like discuss what actually each of the, what these are, kind of in order as a review. So let's just start with arithmetic sequences. Arithmetic sequences have a common difference for them. So let me write that down here, and they're generally taught in that order. So there's a common difference. Okay. So when I look at like this one right here, letter 2, the common difference is 3. That's like the next term, an plus 1 minus an. It should be the same each time. Okay, so but there's all kinds of them, but we'll just write that one there: 4, 7, 10, 13, and so on. Okay, and then geometric's usually the next one that you're taught. So that has a common ratio, and that happens when you divide terms. So like it's now an plus 1 divided by an equals, or well, it's the same each time. So you're looking for things that divide really well into one another. So this one right here, maybe it's not, it's probably not super obvious, but like 6 divided by 4, is that the same as 9 divided by 6?
Yes, 1/3.
Yeah. 3 halves.
Oh, 3 halves.
Yeah. So you check a few of these and make sure that they're the same. Okay, so that's a geometric sequence. And then there's these other ones. The one that I think you and I have talked a little bit more about are these last two, these recursive and then explicitly defined sequences. So the explicit means you get the term immediately, and that's an example of this one right here, number 3, because you put a number in for n, and you get a number out for it, because you just have to put that number into it. It's kind of like a function, I guess you could think of that way. The recursive ones, though, they require you to know something about the previous terms. Okay, so the difference is the explicit is you get the term right away. The recursive means that you need a previous term. And that's what this an minus 1 refers to. Hopefully that's kind of clear.
Yeah, that makes sense.
Okay. Then the last one here, Fibonacci, that's this last one here. I don't know how much you discussed that. We don't have to discuss it at all if you don't think it's going to be on there.
It wasn't when we, like, she didn't mention it when we were like doing our notes in class, so I don't think it'll be on there.
Okay. Number 2 says, does a recursive definition of a sequence always need to give the first term or terms? So the answer is yes. Recursive, we just said that. Recursive requires you to have at least the previous term. It depends on how many it's defined for. There it is. Can't scroll down. So if we created a recursive sequence, we said an plus 1 equals 3 plus an, and I asked for it, and I said, well, let's let n equal 1. You would have a problem here, because a2 equals 3 plus a1, and you don't know a1.
Mm-hmm.
So the previous term is needed there. You could have as many terms as you want. Like you could say an equals 3 times an minus 1 plus 2 times an minus 2, and here you need the previous 2 terms for this,
right,
to be able to do it. So that's does recursive always need? Yes, it does. It needs as many terms as are in here. So like this one would need 2 terms to do it. All right, number 3. All right, number 3. There's a lot going on here. Let's just put some let's just put something in here. If 3n plus 1 over 2n minus 1, limit as x approaches infinity, a sub n approaches 3/2. So I'm filling these in here for you. Do we say that sequence converges? So it does in this case converge when it approaches a real number, L.
Mm-hmm.
Okay. If it doesn't approach a number, L, like if it approaches an infinity, plus or minus, then it diverges.
Yes.
Okay, so that has to be very clear. So then, for example, another type of sequence we might see is like if, let's say it's 1 over n plus 1. This approaches the value of 0, and it converges. And this goes nicely into like what's down in 5a, b, c, and d. We might move to that next, and then come back. Yeah, we should do that. Okay, so the convergence divergence thing is I guess it's somewhat confusing because you have to remember that these things are really like functions, meaning like they have some of the similar properties to them. So let me try to explain that in terms of functions for these. So there were 3 cases for functions, for rational functions. So rational functions was a polynomial of x on top and a q of x on the bottom, and they had all these different properties. So one of them was for horizontal asymptotes. So case 1 said that if the degree of the numerator is less than the degree of the denominator. Do you remember what happens here? The horizontal asymptote.
Oh yeah.
Oops. So I'll fill it in here for you, just to make this text a little bit larger. So what happens is that the thing approaches 0. Y goes to 0 as your horizontal asymptote. So let's look at an example of that here. It's actually letter C. Let me snip letter C in specifically again. So if you look at letter C and you think of it as, if you can imagine it really being a function of x, so f of x equals 6x squared plus 8 over x cubed plus 2. The degree of the numerator is 2 because of that 2 right there, that exponent there. The denominator is 3 because of that 3 there. Since 2 is less than 3, okay, this thing goes to 0. And that means the limit of this thing goes to 0 because of the same reasoning.
Okay, that makes sense.
So the limit, sometimes you have to write this, the limit as n goes to infinity, and you have to actually put this thing into these curly braces, you would say goes to 0.
Okay.
Okay, now let me just make another example here that's really meant to analyze this. So let's say it's 10 to the 99 x plus 1 over 10 to the minus 99 x squared minus 1. Okay, what is the degree of the numerator here?
1.
1. What's the degree of the denominator?
2.
2. So it doesn't have anything to do with like, this is a huge number, this is a really small number.
But it's all like irrelevant in the long term.
Yeah, it's all the time. Since 1 is less than 2, this thing goes to 0.
Okay.
Okay, so then case number 2 here is when the degrees equal, when the degrees are is equal.
And would that be B?
Yes. So it's almost easier for me to just show you what it becomes to remind you, because you already know this. You've already seen this before. But I'm gonna write it slightly differently. I'm gonna write it in f of x notation just for now. 3x plus 2 over 5 minus 2x. But then I'm going to even rewrite it further. I'm going to put the leading term first. So it's minus 2x plus 5. This thing has a horizontal asymptote at y equals 3 over negative 2. It's these two numbers here. So it ends up being negative 3 halves. Same principle applies here. It's the ratio of the leading terms.
Okay.
Okay, so it's 3 over negative 2. You got that. Sometimes it's hidden in there. Okay. Okay, now what to do for letter D? Letter D it's actually the third case. It's what you would refer to as a slant asymptote. Let me snip that in. So let me copy this in again.
So what does that mean for the limit of B?
Let me get caught up to you. We'll say that one more time. Limit of
B.
of B. Oh, it's 3 halves, minus 3 halves.
Okay.
It's
So it
it's this
converges to negative 3 halves.
it's the same thing as the horizontal asymptote. Yes.
Okay.
Okay. So then case 3 is when it's is greater than, and that's what we see in this example down here, because the degree of the numerator is 4, and the degree of the denominator is 1. There's a 1 there. 4 is greater than 1. So this either goes to plus or minus infinity, depending on other factors, which we can explain here in a moment.
Okay.
So your choices are, if we're just reviewing here, your choices are they either go to a number or 0, or they go to infinities. Those are your 3 choices. So the reason this one goes to plus or minus infinity is because the top one is growing so much faster than the bottom one. And then it comes down to, well, which way is it going? Well, all you have to do, if you're not sure, is plug a few numbers in and see whether it's a positive over a positive, a negative over a negative, or like a positive over a negative, or a negative over a positive. And that tells you. So like, imagine you put a large number here. Well, that's positive plus another positive number. So that's positive. Down here in the bottom, it's a positive number plus another number. So that's positive. Okay.
Right.
So it goes to positive infinity. I wouldn't put it past your instructor to give you something that goes to negative infinity. So what might that look like? I'll give you an example of that. A sub n equals x cubed plus 1, negative x cubed plus 1, absolute value of x minus 3. So this one up top here, it's always a negative number, because you cube something, but then you negate it, add 1 to it, it's always negative. This one at the bottom is always positive. So this one actually goes to negative infinity because of that.
Right. Okay, that makes sense.
Okay, so you got to just be careful about your signs. All right, now what about A? We didn't talk about A. A does not have an explicit or a recursive formula for it, but does it look like it's growing to a certain number?
Yeah, it looks like it diverges to negative infinity.
It does. Yep, it diverges to negative. I guess I didn't say that. Whenever you diverge, you either go to positive or negative infinity.
Right.
Now, your instructor could be very crafty, I'll say. There are some functions that actually look like this, where they actually do approach a value. But depending on where you get your information, you might not see that it's doing sort of this thing. So you really have to make sure you're comfortable with the idea of, okay, I'm either going to write the formula, which is best, because if you write the formula, you know what to do. If you're just given a bunch of numbers like you are in this problem up here, you have to make sure that it really does actually go out forever. Because this one could be like 1, 2, 4, and then 8, 10, 12, 13, 13.5. And this number might be 14. I'm just trying to give you some really ridiculous examples to emphasize. See, like it looks like it's growing really fast, which is what happens here. and then starting at 10, it grows less and less.
Okay, I see that. But you like if you had like something that was either like explicitly or recursively defined, you would be able to see that it did that from the equation.
You could, yeah.
Okay.
This one's a little harder to see, but yeah, you could do that.
Okay, that sounds good.
So this one, I mean, this looks like this is something like f of x equals, it's a number over 1 plus e to the minus kx or something like that. And this thing always approaches this right here. I just am concerned you're going to get things that are crazy.
Yeah, I'm concerned as well.
So let's do number 6, and then we'll move on to next one. We can go back to 4 if you'd like. Just let me know.
Okay.
All right. The first two terms of a geometric sequence are 4 and 8. So that means that A1 equals 4 and A2 equals 8. Okay. With a geometric sequence, we talked about this earlier, it is a common ratio R. R is equal to AN plus 1 over AN. Basically the next over the previous. So that's 8 over 4, which is 2.
Okay.
So do you know the formula for a geometric sequence?
I've seen it.
Okay.
I should know it.
I don't remember. Do you get an equation sheet on there?
Oh, I get a full sheet of paper. So if we can use the last like 10 minutes for you to be like, oh, this is exactly what you should have on there for this part.
Okay.
That would be kind of fun.
Yeah. So this is one of those things that you would want to have on there. And yeah, we'll do that. So the formula requires you to have A1. Well, hey, I've got that. R, you got that. So AN equals 4 times 2 to the n minus 1 power.
Okay.
So if I wanted the 6th term, A sub 6 means the 6th term. That means n is 6. It's 4 times 2 to the 6 minus 1 power. So that's whatever, 4 times 2 to the 5th. That's 4 times 32, which is 128.
Okay. That sounds good.
Okay. Let's go to number, do you know if there's a calculator section on this?
I know that for some of it, I will be allowed to use my calculator, but she doesn't tell us for what.
Okay. This one says to use a calculator. I mean, it can be done by hand. It's just kind of long. Let's just say, let's just change up a little bit. Let's just say to evaluate partial sums. Have you heard that terminology here?
Yes, I have.
Okay, so the first thing is we can just write out a few terms. We can say, okay, let's say k is 3. That means that it's 9 squared minus 2, which is 7. So your first partial sum, your sum of the first term, which is really when k equals 3, which is kind of weird, but we'll just do it like that. The sum is 7. That's a partial sum. Let's say k equals 4. That's 4 squared minus 2, which is 14. S sub 2, which means that k is 4, is 7 plus 14, which is 21. Okay. And then k equals 5. This will be the last one we do like this. 5 squared minus 2 is 23. So sum 3 is k equals 5, and then it's 7 plus 14 plus 23. Okay. Now, what might your instructor do? So let's just make one up here. It's a little bit different. I noticed. Let's just say it was natural log of k plus 2 from k equals 1 to 10. Okay, your instructor could say to use a calculator here, but the problem is calculator will just give you decimals, and your instructor might not like that.
Right.
Okay, but I guess first thing is, do you know how to find the sum in your calculator? Do you know where to go to sum, sequence?
Yes, I do.
Okay.
Okay, so.
So let's not go to 10. Let's just go to 3 for your calculator, please.
Okay. Okay, so I definitely forgot where this is on the calculator.
Okay. Let me do some quick searching to find something to snip in here. I think it's under math button. You're using an TI-84?
Yes.
Okay.
Oh, got it. Math 0.
So the sequence is different than the sum. So that's the I guess the maybe the difference here. Yeah, math 0 gets you the sigma, and then like to me it looks like on your calculator you can do sigma x equals 1 to 3 natural log of x plus 2.
Mm-hmm.
Okay. Did you get a number for that?
Okay. One plus 2. I got 4.0943.
Okay, so around 4.09,
Yeah.
etc. Okay, so let's do the first sum. So the first sum is the natural log of 1 plus 2. Could you just calculate that in your calculator?
Two.
Say that again, just 2, right? So
Yeah.
a question, I mean, it's not on here, but your instructor said, well, how far away is the first partial sum from the total sum? And it's a lot away. So then the second partial sum would be or I'm sorry, the second term. Well, so you can
Oh,
try.
I put in the full sum wrong. It's actually 7.8-ish.
Okay. Okay.
Yeah.
Whatever it is it is. So I want you to find the second sum, and that's you can do that by going sigma x equals 1 to 2 natural log of x plus 2 and getting that number if you want. So we can build up these partial sums. So like I guess part of me just wanted to get it comfortable with doing the calculator, but I think I wanted to make a point here. So
4.7.
yeah, 4.7. Okay, so let's just say I gave you. Well, I don't know. I'm going off, and we need to be more practical here today. Let me just jump back to what you sent, and so you can do stuff in your calculator, which is the point there.
Okay.
Okay, let's do number 6 because it's kind of a calculator question, but you may not have a calculator for this. So I want you to enter this into your calculator again, but instead of infinity, this is what we should have done. Instead of infinity, let's do it for 10,
Okay.
20, 40, and that probably will be enough. So give me the values for each of these, or I want you to see if you notice something as you do this sum, and you're going to use x instead of k for each of these values.
Okay. For the first one, I got 7.999999.
Okay. The next
And
one.
for 20, I got 8.
Okay. You probably get 8 for 40.
Okay. I also got 8 for 40.
So without knowing anything, could you convince someone that this converges?
Yeah, because the calculator doesn't show enough digits, I
Yeah,
guess, to
exactly.
show that
It goes to
right?
the same value basically every time. It's exactly right. Now, um, so we need to just step back for a moment and talk. I think I may have drawn this diagram for you previously. So that there's all sorts of these sequences, and that's what we kind of started out the day with. But the two that you mostly care about, and this is kind of the start of what could go on a reference sheet, is you can go down this path of there's arithmetic sequences. And for an arithmetic sequence, you can write a formula. You can write an explicit, or you can write a recursive formula for each of them. Okay. When you know the formula for an explicit, you can always find a finite sum for it. Okay.
Okay.
Now, the other types of sequences, this is where we'll get back to what we're actually talking about in this last problem, geometric. You can do the same thing. You can write explicit and recursive formulas. Now, the explicit formula, there's actually two types of sums you can find. You can find a finite sum, and you can find an infinite sum in some cases. So this problem we just did, the problem number 6 here, where we're finding the determine whether the series converges, we're going down the path on the right where it's a geometric sequence, we have an explicit formula, and we actually can find an infinite sum here for it. Okay, so let's do this now. Let's let k equals 1. Okay, k equal 1. And then what is the value of this sequence? Well, just this part, not the sum part. Well, it's 6 times 0.25, k to the minus 1, which is really 1. So this ends up equaling 0. Let's let k equal to 2. A sub 2 is 6 times 0.25 to the 2 minus 1 power, which ends up equaling 0.75 times 6, which is 4.5, I think.
Right.
Okay. And this is enough to find r. So r is equal to 4.5 divided by 6, which is, oh, I wrote the wrong number. This is 2525. So it's 1.5, sorry. Get the wrong number there. 1.5. And this is a 1 here, and that's 0.25. So you might have said, oh, I should have known that this is r right there. And since a1 was 6, that's the first term there.
Okay.
So this right here is the summation of an infinite geometric series. Infinite geometric series right down here. So the sum of this, if the absolute value of r is less than 1, r is the ratio between terms, the sum is equal to a1 over 1 minus r.
Okay.
So how does that help us here? Well, the sum here is a1, which is 6, over 1 minus 0.25. So that ends up equaling 8.
Okay.
So let's just see if you got that. So you want to have this formula down. Let's say I want you to find sigma -2 0.375 to the k minus 1 power. I want you to find the sum from 1 to infinity of this one, please.
Okay. Negative 3.2.
So it should be -2 over 1 minus r, which is 0.375.
Right.
Is that what you did?
That is what I did.
Okay, and you get some number here. Great. Now, what is the sum from n equals 2 to infinity on this one? So this is what your instructor might ask you, because your first term is no longer this. Your first term, you actually have to calculate the first term. You have to actually put n equals 2n to get -2 times 0.375. Sorry, that's a k, to the 2 minus 1 power. So you actually have to get this number.
Okay.
And this is 3/8. So it ends up being a negative
0.75.
yeah, negative 0.75. So that's actually, this is now your A1.
Oh, okay. So
Because
then
it
you do.
starts at 2, yeah. So your sum here would be negative 0.75 over 1 minus 0.375, whatever that ends up
And
being.
that only works if the absolute value of R is less than 1, right?
Yes.
Okay.
So I mean, I wouldn't put it past your instructor, but like it would be something like, let's say it's 0.2 comma minus 0.4 comma 0.8 comma minus 1.6, and your instructor said to find the infinite sum of this thing. Okay, so the first thing is you gotta know. That's why I go back to this path here. What kind of sequence is it? Because there's only one infinite sum that you know how to find, which is if it's geometric.
Right.
So is this geometric?
Let me check.
So is it geometric? So is minus 0.4 over 0.2 the same as 0.8 over minus 0.4, the same as minus 1.6 over?
The common ratio is -2.
Common ratio is -2. Okay. Now maybe now you're like, oh, well, that's Matthew. That's not less than 1. You said it had to be less than 1. So this one does not converge. But can you see how on an exam you might not remember that very quickly, and you might say, oh, these numbers are small, my infinites, because it actually works out kind of nice here. 0.2 over 1 minus a minus 2. Okay, I get 0.2 over 3. I'm a happy student here. It's 1 over 15.
But no.
No, this is completely wrong, but it looks right. So please try.
Exist.
So please try to remember that you can only find an infinite sum if it's geometric and R is less than 1. And there's many ways to mask this that you may or may not know. There's some things you can do with natural logarithms also to hide it, but that's something to think about. So now we didn't really go down this arithmetic loop at all, but that's you can find a finite arithmetic sum.
Right.
Okay, and to do that, that sum is n over 2 a1 plus an.
Okay.
Okay, now let me come up with something here. Let me just need 30 seconds here to come up with kind of a more challenging one. Ooh, that didn't work. Sorry, that didn't come out the way.
Don't worry about it.
There it is. Okay, so I made up a kind of a really awful one here, where I give you the first few terms. I tell you the first term is 1.3, comma 2.1, comma, and so on. Actually, let me give you one more, 2.9. And I want you to find the sum of the first 127 terms.
Okay. So it looks like there's a difference between 0.8, right?
Yes, there's a 0.8 ratio, a difference of 0.8. Okay, so now this one actually is asking you to do a couple of things that generally when you get tested on you have to do. So you have to realize, okay, this is arithmetic. You already did that. You really need an explicit formula. Why do you need an explicit formula? Because not only do you need the first term, you need the last term.
Right.
Okay, and then you need the number of terms, which I've already told you. So you really need the formula here. So the explicit formula is an equals a1 plus n minus 1 times d.
Right.
So can you get that here?
Yes.
Okay, so you have an equals 1.3 plus n minus 1 times 0.8.
Okay.
So can you find the 127th term? Yes. Then you need to use the formula to do this. And then we'll do another one that's a little bit more difficult.
Okay, so 102.1.
Check that. Oh, I went to the wrong. I went further than that. Yeah, that's right. Okay. A 127. Yes, 102.1. Okay, so that gives you, so you know that the sum is 127 over 2. A1 is 1.3 plus 102.1, I think you said. Yes, there it
Yeah.
is. And then you add it up and get that. Okay, so that's kind of one variation on it. I could, okay, so let's just say I gave you another sequence here. I said, okay, it's minus 1, 1, minus 1, 1, minus 1, 1, minus 1 forever. And I wanted the sum of the first 100 terms.
Okay. So
is this arithmetic? Is it geometric?
it looks like it's geometric.
It is geometric. It is geometric. So now we've gone down this path where we actually haven't talked about how to find a finite sum yet, which we will do, but I want you to notice something about the partial sums here. Like if I asked you what's the sum of the first two terms, you would say
0.
0. First three terms is minus 1, but four terms is
0.
0. So this one is 0. But if I said the sum of 1,001 terms, it would be
-1.
negative
Okay, that
1.
makes
Okay.
sense. So you
So
don't
now
need
how could your instructor put this into a question? Well, they might want you to write some sort of explanation for like, well, or they might want, or this, I mean, the more difficult one is write a sequence that sums to 1 if odd, 0 if even, something like that.
So then you would find the like equation for a partial sum and then like reverse solve it, I guess.
Well, I'm trying to get you to see like you can do some things with numbers like this.
Yeah.
So if it's odd, if it sums to 1 if it's odd, or 0 if it's even. So the even one's pretty easy. It's
Right.
minus 1, 1, minus 1, 1. But if it's an odd number of terms, what does this sum to?
-1.
Negative 1. So that doesn't work. So what if we switch the order?
Oh,
Now does it
yeah,
work?
that's a +1.
Okay. Now your instructor would be more difficult and say, like, I don't want you to use 1s and negative 1. So you'd have to switch to like 3 and negative 2. That's where it sums to positive ones. Like your instructor could see things like sums to 1 for even, sum to 3 for odd. And you may just have to play around with some of these things. But this is called an alternating series. I mean, you didn't cover it, but I mean, I wouldn't, from what I understand, your instructor might want to do that.
Yeah.
Okay, we're about 10 minutes away. You said you wanted some stuff for this. So for the sums, the real things that you need for the sums is you need to, you start from the top here. And let me grab, I would, the thing that's missing here is, and I thought we did this before, is like how to write a recursive and explicit formula for each of the
Yeah,
types.
that would be good. Yeah.
Okay, so okay, so we'll call this your note sheet. So your explicit formula for, and we're doing this for arithmetic. Okay, your explicit formula is an equals a1 plus n minus 1 times d. Your recursive formula is that the next term equals the previous term plus the common difference.
Okay.
And then you can do the same thing over here for geometric. The geometric is that an equals a1 r to the n minus 1 power. An plus 1 equals r times an.
Okay.
And you, I would verify. No, I mean those are fine, but you know, having the form is great. I mean, you'll get a few questions where you have to do that, but not too many. And then the sum here, the sum for n terms is n over 2 a1 plus an. The infinite sum, that's the more common one, is a1 over 1 minus r. You can do a partial sum here of these. Let me look up that formula. Geometric series, non-infinite sum. So it's a1 1 minus r to the n plus 1 power over 1 minus r. Maybe you've seen that.
Yeah, I've seen that.
Okay. So this has no limitation, because you can always, the idea is the idea with these two is you can always add up a fixed number of terms. It's like if you got 10 fingers or whatever, 8 fingers, 2 thumbs, you can count. Like you can count those. But if you had something that just goes on forever, you can't count them because you can never get there. But these two, as long as you do that, it works out. So I mean, and that's, I hate saying it, but that's all there is to say about these. There's other sequences that we talked about. We did not talk about Fibonacci, but I did show you these sort of alternating term sequences.
Yeah.
There's the recursive ones. Okay, so those are some things to think about having on your sheet. So now let's go back to talking about what is in the first few sections, which is vectors.
I also have a second session with you today.
Oh, okay.
So that will happen there as well.
All right. So what else can we do with sums then? Sorry, I didn't look ahead on my schedule. Really, sometimes I just try to do my best. So these convergence, divergence, the idea here that there's kind of 3 cases, I would probably put that in.
Okay.
Your instructor, though, does not really. You would do really well if these were more mechanical problems where you just here's a rule and apply it. But there's these 3 cases. Case 1 is the example is like n over 3n squared minus 4. This one goes to 1/3 because there's a 1 there and a 1 there. Case 2 is something like a 4 minus 3n over 5n plus 2, and this goes to negative 3/5. And then case 3, it looks something like, let me give you something even crazier. Sorry, I got to think about it. So these are things that are covered in like calculus, second semester calculus. Which is,
yeah, I was just about to ask about that. She had a practice, like on her notes, she had a problem that was like, oh, what is the sum of infinity sum k equals 1 sine of pi n?
okay, we're going to answer that, but kind of do this. So whenever you see sine and cosine, you have to remember that they are bounded from -1 to 1. So the biggest value they can take on is either -1, +1, or -1. So like that thing's just moving between -1, +1, -1, but this thing's growing forever.
Right.
Okay. The problem is, though, you actually don't know whether this is going to positive or negative infinity because of this alternating. So let me actually do this. I have to put this in absolute value. So that way it's always up above 0 here. And then this goes to positive infinity. Because n squared is bigger than this thing.
Okay.
Okay, I don't think that was clear, but what's the one you're giving me? Sigma, sine, pi n?
Yeah, sine pi n, and then infinity over k equals 1.
Okay, cool. So these are read and written from bottom to top. The problem with this one is, like, again, it's not, you have to go down that map. Is this arithmetic? Is it geometric? And it's neither. So you don't know how to find these. There are other tests, but they're in calculus 2, which you're not doing. Sine pi n just means like this thing looks like this. Now there are certain partial sums that you could find. Like this area above is the same as the area below.
Yeah, she had a similar one where she wanted the partial sum of that, but to 12.
Okay, so like you gotta find these nice breakpoints, and that's like pi over 2 and pi, and so from like 1 to 1 is 0.
Okay. Yeah.
But then when you go out further, it's not.
Right.
Like when k is, well, actually k equals 2. I mean, if it's out here 2 pi, then it is 0. Oh boy. How about this? Let me just get your feeling on this one. Sine pi n, if your an equals this, over e to the k, I'm sorry, e to the n pi.
Okay.
I'm going to tell you that this converges, so to maybe help you. If you just looked at these individually, what does sine pi n move between?
1 and -1.
1 and -1. E to the x, it's going from 0 to infinity.
Right.
This is completely wrong. This is like magic math or whatever. It's not notationally correct, but it helps to answer this question. This thing on top is bouncing around from 1 to -1.
Mhm.
What is a number over infinity? Because that's what happens is
0.
0. So sometimes doing this can help you answer these questions where you sort of say, I think it's in this window.
Okay. That makes sense.
All right. So are we going to cover vector stuff in the next session?
Yes.
Okay. I don't have time to do it, but I want to ask, did number 7 get covered in your class? Like, was this a point of emphasis, writing these repeating decimals?
No,
Okay.
not at all.
All right. It's a very specific thing. So
She's
if you, okay.
She will not ask that.
All right. Okay. Well, that's it for now. I'll send you the notes and screen recording out. Probably won't do it until sometime between 12 and 1, and then I'll.
Oh, okay.
But I'll send them out to you at the time. So thanks, and I'll see you in a few hours.
Thank you so much.
You're welcome.
Bye.
Bye now.